Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about carbon fiber. So let's dive right into it. Now, first thing we have to understand, we are talking about a composite material. It's not just one thing, it's always a thing plus a mixture. Now, think of it this way, like how concrete is just not concrete. Generally, there is a rebar, generally there is sand, generally there is aggregate, and then you have cement. So that is a composite material. So this is also a composite material. Whenever people are talking about carbon fiber, they're not talking about carbon raw fibers. They are generally talking about carbon fiber composite, but that's a long name, so people have shortened it to carbon fiber. So it generally includes of carbon threads, which we call carbon fibers, and then binder. So binder is not cool, so we simply call it carbon fiber. Now this puppy is very strong. Now that's not a big achievement. We have strong things, we have buildings, bridges, rockets, things and of that nature. So building strong things is not that amazing. However, this puppy is light. Now to give you a context of that, if you are designing something like this, where it's like, let's say you want to make a tank, let's say it's a tank for firefighters, where you want the tank to be as light as possible, this puppy will flat out destroy any metal alloy that you can think of. And I truly mean anything, as in like even titanium and all that jazz. So flat out, this puppy is very strong while being very light, which is very unique and very hard to achieve in anything other than carbon fiber. Then we come to another aspect. This is corrosion resistant. What does that mean? Think of it this way, let's say you made your aircraft with this thing. How long can it endure the elements? This puppy will last much longer than anything else. Now you may be like, hey, aluminum does not corrode. Well, it does corrode. It does form a oxidization layer that protects it, but it does form a layer. Over time it could erode. And not to mention, if you have talking about salts, or which are generally used in places where we have a lot of ice, those things will over time, not in one day, but over time they will corrode it. Compared to that, carbon fiber is like, who cares? It's like it is very idiotically corrosion resistance. Then we come to another aspect of reality is like, if you want to achieve certain unique properties, there is no better metal alloy. You cannot mix two metals that will come even close to this. Let's say, for example, you want to make a rocket, let's say electron rocket out of lithium aluminum alloy. This is commonly used by SpaceX and all other space companies. It will still not be able to match the carbon fiber composite. So fundamentally speaking, this is one of the best materials we have. Now let's understand with the core level, the carbon fiber, the name exactly. Now you start with good source of carbon generally. Now it's generally polyacrylate, something like that. Basically you have a long chain of carbon bonded with nitrogen, or sometimes you could use other hydrocarbon also, like pitch, generally byproduct of petroleum industry. And sometimes people are researching on a ways to providing that carbon source from wood also, so creating some other sort of base. Now you start with that puppy, and then you basically cook this. Now your cooking start is generally called pre-treatment. Now pre-treatment will happen at around 300 degrees Celsius. So basically you will start that, and you will start to make it into some sort of a thread, doing whatever machines you utilize. Basically think of it this way, how you make cottons into threads, you start to do that same process. Now you will try to oxidize it. What does that mean? That simply means anything that is willing to bond with oxygen, that is free floating at 300 degrees Celsius, you just want to get rid of it. Basically if you have hydrogen there that wants to bond away, you're like, take it and go, leave the carbon, take the hydrogen. Why? Because it's 300 degrees. If it was very high temperature, it will flat out burn it. But if it's low enough, things that are more reactive or more volatile than basically carbon, they will react. And carbon is stable here because it is in a molecular chain configuration, so it's more stable. Now that's your first thing, that's the step one, that's level one. Now you bake it. Now you have cooked it, you bake it. Now baking it generally requires an inert environment. Now in your inert environment, you're gonna increase the temperature. Now you're gonna send this puppy up to 1200 degrees Celsius. Now this is some serious temperature, and you have to make sure you do not have oxygen there, simply because at those temperature you are reaching a point where you can burn diamond. So now you have something that, like, that you first, by cooking it, you remove the impurities. Then by basically baking it, you made the carbon chains to bond with each other, and during this process they try to remove as much impurity as possible. Now this happens on a chemical level. It's not like you are going there and doing something. It happens on a chemical level, and it tries to bond it. Like at this point in time, it's almost reaching graphene level of polymer chains, but it's not that perfect, but it's reaching there. It's like almost to a point where it's like every carbon atom is bonded to itself. So it's very awesome, at this point in time. Now there itself you can be like, okay, done, I'm packaged, you can sell it. It will be classified as type 3 carbon fiber. Then you can do another stage of heat treatment where you will try to carbonize it a bit more. Basically, how much, no matter how good your cooking process is, no matter how good your baking process is, there still would be impurities. So at that point in time, you will have nitrogen, hydrogen, things of that nature. Basically, you will have a lot of impurity. But this is more than good enough at this point in time. This flat out, if you went into 1990s, this will be wonder material. So this is type 3. Then you do some another processing where you heat it for much longer. Basically, same temperature, but you cook it for much longer, and then you can achieve type 2. Now this time you replace the inert gas from nitrogen to argon, because nitrogen at very high temperature does start to react. So you want to replace it with something bit more stable. Argon is generally a good system. That will give you type 2 carbon fibers. Then we come to aerospace grade carbon fiber. There you do the same thing. You take the inert gas, but this point in time you are trying to make it directly into graphene, and this point the temperature goes up from 1700 degrees Celsius to 2800 degrees Celsius. Yes, there are very few kilns that can handle that kind of temperature, and at this point in time you put as much temperature as you can, as much pressure as you can, and then you get type 1 carbon fiber, the latest and greatest, also the most expensive. So that's the whole point. You start with a polymer source, then you remove easily removable impurities, then you bake it. Baking process bonds itself with itself. Now that's good enough, and if you are happy with that, take it and leave. And if you are like, no, we want more power, then you will like basically bake it even more time. Try to basically make it as close to graphene as possible. So that's carbon fiber. That's how you get the quote unquote carbon fiber. This is not glass fiber. This is not polymer fibers. These are exact carbon fibers. It's like almost 98% up to 98% raw carbon. So this is almost pure carbon. And that's why the temperature has to be like in a inert environment, because carbon does burn. And if you are reaching 2800 degrees Celsius, you will burn basically diamond without any issue. Then we come to the binder aspect. Now one thing you have to understand here, can your house be built out of bricks? Most people will say yes, but the answer would be no, it cannot, because bricks itself will not bond to anything. You need bricks, then you need cement. Same way here, binder is playing that same role of the cement. Now this is the weak link in the chain, because this puppy is almost touching the same strength of diamonds. It is like inherently carbon well bonded to itself. It's very strong on a molecular level, and you're talking about long threads of this puppy, you're talking about some GG materials. However, this is a cloth material. You are making a cloth out of it. You're not making any structure out of it. You can't make it into rods or shaft or things of that nature. So to make sure we get from basically fiber, basically like cloth, something like that, go into solid form, that we need binder. Now binder is the weak link. You could literally have a scenario where you have type 1 carbon fiber, the latest and greatest, made from Japan. Japan is the world leader at this point in time. And you are like, awesome, this is going to be the awesome. But your binder is not really, not of high quality. Yeah, you're gonna have weak structure. Or you could even do invert. You can buy basically level 3 carbon fiber, which is not the greatest, but like more than good enough, and you're like, okay, I'm gonna put the most awesome binder into that. You're gonna get amazing strength. Now what do we use in binding? Well, this is where top secret part comes in. Generally people use epoxy, resin, or some other types of polymer. Now how they mix it, how they basically cure it. Sometimes they use UV to cure it, sometimes they use heat and pressure to cure it, sometimes the reaction itself is exothermic, that gives off heat to cure it. So this is like where the secret sort begins. This is the part where like Boeing engineers are like, only the people who are classified, organized, like have the highest level clarity will know what exact mixture is. Now you can get these things on your home. Basically even a normal basic epoxy will do the trick, resin will do the trick. It's just like to get that extreme power to weight ratio, you need the best binder out there. And be mindful, this is the weak link. So if you have weak binder, it's not useful. So do not think that you can make a carbon fiber fuel composite. Like, can you make a carbon fiber fuel composite? Absolutely. Can you make it as awesome as a proper corporation working on it? No, simply because your binder will be the weak link. Now how do we get, now we have something, how do we make something out of it? It's like you have brick, then you have cement, then you have to make a house. That's a big process. So this is not sold as a like pellet material. It's not like, okay, big aluminum goes into CNC machine routes out everything. It does not need tada your engine block. That's not how it works. So there are many processes of making actual finished part with this puppy, and they will give different properties. So if you are going to someone, hey, give me something that is like super duper hard, like this puppy is supposed to be as hard as possible. There will be a different process there. Then you go to something like, dude, I want this to be strong, but it should flex. It should not resist flexing, but it should be as strong as possible. Then there will be a different process for that, and all of them will amount to different casing. So yes, you can buy carbon fiber iPhone cases or Note cases, but those are not high grade aerospace grade carbon fiber, because while the carbon fiber is true, most likely it's grade 3 carbon fiber, not grade 1 carbon fiber, and the binder is very low grade. So I'll give you two primary examples that is generally utilized. So you have carbon fiber cross rolled. What does that mean? That simply means, let's say you have a shape, let's say a tube or a fuselage. Then you wrap this puppy up as much as possible, like depending on how much thread you want to utilize, you will wrap this puppy up. Then you're gonna add binder. Now this binder will generally be applied while you are rolling it also, so it has a proper penetration. So you have one layer, then there is a binder, then you have another layer, like same way we built bricks and cements and all that jazz. Then you put it in autoclave. Now this is the point where most people basically give up on Kevlar fiber, because this puppy is idiotically expensive. Because when you are talking about autoclave, what you are talking about is something that can go hot, as in 300 to even 500 degrees Celsius. Now that's not big of a deal, that's super easy to do. However, it's supposed to do it in pressure. For example, Earth's atmospheric pressure is around 15 psi. Awesome, not too bad. This puppy can easily go up to 500 psi. 500 psi at that kind of temperature, it's a big boom chamber. And if your chamber had any kind of failure, this will actually go boom like this. So fundamentally speaking, that's a big boom chamber that you have to build. And autoclaves are idiotically expensive. So if you want to build a small autoclave that is like designed in such a way that it can handle the biggest single part of your car, awesome, that's not too expensive. The moment you go to something bigger, company would be like, yeah bro, this is gonna cost, like instead of $1 million, it's gonna cost billions of dollars. To give you a context, the biggest autoclaves in industry at this point in time is utilized in aerospace industry, and it takes years to build. Like just a chamber that is strong enough, robust enough, and insulated enough where it can keep the temperature and the pressure, it takes insane amount of energy. And this is the point. So if you are thinking about, hey, why didn't people build Airbus A380 with autoclave? Yeah, think of this, like Airbus A380 is huge. You have to build a chamber that is even more huge than that. So there are limitations to this. Then we come to another aspect is which is for basically low cost building. You start with fiber, you start with binder, then you make it into sheets, and then you apply the sheet into molding. I have provided a video down below, a person doing this. It is something doable in home, quote unquote. And then you put it in mold, and then you vacuum presses. Now vacuum pressing will do the job because atmosphere is 15 psi, and 15 psi uniformly applied everywhere. That will make sure you have good penetration of the binding agent. So binding agent will cross-link properly, then you won't have the sheet will delaminating, how bad plywoods have. The sheet starts to delaminate, you won't have that. You can do amazing things with that, but be mindful, that's nowhere near strong enough as autoclave parts. A properly done autoclave part would be like damn near indestructible. A properly done vacuum press part would be a bit better than aluminum, bit better than steel, but don't expect too much out of it. It's like it's good, but not, no close but no cigars, so to say. So that's why you can have a scenario where it's like, dude, how the heck this material is so amazing, so expensive, why the heck I can buy a bicycle out of it, or iPhone case cover from that, simply because they are utilizing different process. Now, how do we utilize this magic material? Well, reality is generally most time people will avoid it, simply because even if you can do a thing, for example, SpaceX, even if they could figure out how to make the goddamn thing, which they never did, the tank was not made in one piece, it was made into two segments, because I'm pretty sure the autoclave was limitation. And there are some people who are developing system that does not require autoclave, but it's not as strong as like other systems. They are utilizing laser to basically spot clave it, quote unquote, spot bake it. Benefit, it does make it far more manageable, but the consequence, you have to do an extra ultrasound test just to make sure there are no micro voids, because that would be the place where things will fall apart. So you have to be very willing to let just money go. You have to just let the money go. You don't think about it, just let it go. If you can do that, then only you talk about this. So aerospace industry, big example being fighter jets, where the money is no object. They're like, just make it out of it. Now small aircrafts, people are trying to make it simply because autoclaves are much more feasible and the total bulk requirement is not too high, so it's doable. So aerospace industry, and because of the fuel cost rising, it does make sense. Like yes, your plane will cost flat out twice as much, but if it saves let's say 20% fuel every month of operation, over time it will pay itself. So fundamentally people are paying huge amounts of money for aircrafts to be made out of this thing. Then we come to another aspect far more practical to day-to-day life, you and I, because I will never see this puppy ever be used as a mass production car element, simply because it's too unwieldy. For example, if you come go to SpaceX, why I'm saying space, Tesla, you go like, Tesla, can you make a supercar? They're like, awesome. Which material would you choose? Steel is too heavy and too reactive, it corrodes too much. Then you will make aluminum. Now aluminum is not as strong or as awesome as carbon fiber, but it does have the benefit. You take a chunk of aluminum, you press it, tada, your whole chassis is done in one go. Take it and go, take it and go. They have figured it out. That's the whole point. You take it and go. But compared to carbon fiber, it will take them months, and that's why most companies that make carbon fiber cars, most of them are bankrupt. Basically, they have been sold to this company, to that company, to that company. It's very idiotically, unbearably expensive. So generally the best use that practically matters for you and me is concrete. Now you're like, wait a minute, I said this is too expensive, and why the heck I'm putting it in concrete? Well, think of it this way. Bridges are idiotically expensive, and what's more expensive than bridge is the maintenance of the goddamn bridge. So in those sort of scenarios, you have to understand this way. Concrete, awesome, but not very good in stress. Steel, awesome in stress, not very good when it oxidizes. Now you're like, how the heck steel bars that are inside concrete, they are oxidizing? Well, Earth's temperature is gonna have to deal with you. Basically, in daytimes it expands, in nighttime it contracts. Now it's a micro contraction and expansion over days. Now that's not gonna break your concrete apart in one day, but over a week, over a month, over a year, over a decade, it will form cracks. Now those cracks allows humidity, basically moisture in the atmosphere, to touch, make love to the rods. Now those rods end up getting overexcited. They start to swell up. Now your structure basically structure is being weakened from the inside, because the steel that's supposed to provide its strength, it's now pushing it from the inside. It's expanding because oxygen molecule is making love with iron molecule, so it's expanding. So it's not only removing the structural integrity it had, it's also compromising it from the inside. So inherently many people are starting to use carbon fiber rebars. Now benefit of these things are, if you are building a bridge in a place where it's a very earthquake prone, this puppy is almost compulsory nowadays. It's like, dude, we have to utilize it, because if you can make it out of strong steel and all that, but it will corrode over time. So maintenance cost over, like, let's say 50 years will end up in a point where it's like, dude, it would have been cheaper if we had just put it there. That's why many people are utilizing carbon fiber systems, and it also makes it lighter. So the lighter it gets and the stronger it becomes, the more resilient it becomes by definition. So that's why making it light is also beneficial. And then you have the low grade concrete, where people are like just putting carbon fibers into that, not complete rods or strands or net or something, like just raw fibers. Now that makes sure it fights against basically micro fractures and all that jazz. Now again, that's not as strong as this, like having an actual core of carbon fiber, but it's better than nothing. So a lot of use in concrete industry. So now be mindful, this is non-recyclable, same way paper is non-recyclable. Now you're like, wait a minute, I heard of recycling paper. Problem is, paper, if you look into like microscope, you will find there are strands. Now every time you recycle it, the strands become smaller. So that's why you will find the paper that is quote unquote virgin paper generally is very robust. It has a sort of strength to it. Why? Because it does not require too much binder. Compare that to basically recycled paper. They have to redesign the binder in such a way that it can compensate. Think of this, like your brick broke. Can you use the broken bricks to make a house? Yes, but it will, cement consumption will go up. So same thing will happens with the basically building cement, and same thing will happen with carbon fiber. So you can have a grade 1 carbon fiber that is like super long, immaculate thing, but once you grinded it down, you can't make it as strong as, like, continuous woven chain. Flat out, forget about that. Now of course you can have like, hey, this was grade 1, once I have grinded it down, I can easily make sheets that are like, say, Mark 2 or Mark 3 level. You can do that, but it will always go down. It's not like aluminum where you can scrap it and get raw aluminum out of it. Do not expect it in that way. So there are uses of this, but be mindful, cost is of no matter. Like, money doesn't matter. Only then think about this. Without that, it's almost useless. So this was my presentation on carbon fiber. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.